Hello students, good evening all of you. In this session let us discuss the ortho effect in carboxylic acids. Okay, I mean we can see this ortho effect in derivatives of the benzoic acid. So generally acidic nature of carboxylic acids or any organic compound is depends on the stability of the conjugate base. This conjugate base is formed after removal of the proton. Okay, nothing but anion actually. Okay, if that anion is more stable, the corresponding the respective organic compound is a more acidic in nature. Okay, so generally conjugate base is the anion, so anions are stabilized by the minus I groups and minus M groups. So here the presence of the minus I and minus M groups increase the acidic nature of organic compounds. Now here, so different from that minus I effect, minus M effect, here the although effect in carboxylic acids. Okay, it's a different case. It's nothing but steric inhibition of resonance. So here in this case, steric inhibition, because of the steric inhibition of resonance, here carboxylic acids, some derivatives of the benzoic acids are more acidic. Okay, so we will discuss that what is the ortho effect actually. Okay, see this one. First of all, here formic acid and benzoic acid, which is more acidic? Formic acid is a more acidic than the benzoic acid, because here after loss of the proton, this is the conjugate base. Okay, after loss of proton, this is the conjugate base. Here this conjugate base is stabilized by the resonance actually. This conjugate base is stabilized by the resonance. So here there is a dispersal of this negative charge. There is a dispersal of the negative charge. Just here two resonant structures are possible. This negative charge is involved in a conjugation with the C double bond O group. Again here this negative charge involved in a conjugation with the C double bond O group. These two are the equal resonant structures. That negative charge is involved in a resonance with the CO group only. That means here there is a maximum dispersal of the negative charge in this conjugate base. That is a formate ion. Now here let us see let us check the stability of the conjugate base. C double bond O, here O minus. Okay. Of course it is also stabilized by the resonance with CO group. Okay. That CO group attract the negative charge, that means here O minus double bond O. Okay, so here this negative charge dispersal. Okay, there is a dispersal of the negative charge. Here in this case, actually, here dispersal of the negative charge is less, but here the dispersal of the negative charge is more effective, because the CO group is only involved in conjugation with this negative charge. But here in this case, the CO group is not only involved in conjugation with the negative charge, here that is also involved in conjugation with this benzene ring. Okay, so here the benzene ring acting as a plus sum group, the benzene ring acting as a plus sum group. Okay, generally here because of the plus sum effect, acidic nature decreases, and because of the plus sum effect here, this anion stability decreases, because in this case this CO group is not only involved in conjugation with this negative charge, also involved in conjugation with this pi bond of the benzene ring. So here the extent of the dispersal of the negative charge decreases, but here in this case the extent of the dispersal of the negative charge is so much effect with the CO group, because this is the only group involved in conjugation with the negative charge. Okay, so there is a 100% dispersal of the negative charge, but here in this case this negative charge is not so much dispersal, because the CO is also involved in conjugation with the benzene ring. So this conjugate base is less stable when compared to formate ion. Okay, this formate ion is more stable conjugate base than the benzoate conjugate base. Okay, because this negative charge is not 100% dispersal, because the CO group is also involved in conjugation with this one. So simply we can say this is acting as a plus sum group. So because of the plus sum effect, your anion stability decreases, so acidic nature decreases. That's why benzoic acid is less acidic than the formic acid. Now here, if you introduce any substituent at ortho position, okay, if you introduce any substituent at ortho position. That means here any group. Okay, that the ortho substituted benzoic acid. Here in this case, because of this group, okay, you can see here in the main point C double bond O, here O minus, here G actually. Okay, group. So because of this group repulsions, okay, here because of the repulsions, here in this case this group is go out of the plane. Okay, because of the repulsion, steric repulsions with the group which is present at the ortho position, this group go out of the plane. So here the resonance with the benzene ring is stopped. Okay, so that means here by introducing of the one substituent at ortho position of the benzoic acid, here the plasma effect of the phenyl which is working in this case here stopped. Okay, that means here this negative charge is 100% dispersal. There is a 100% dispersal of the negative charge with this CO group. Okay, that means here this is a more stable conjugate base because the plasma effect of the benzene ring is not working with this anion, but here the plasma effect is working with that negatively charged, that means a CO group. Okay, so here plus sum effect decrease the stability of the conjugate base, but here the plus sum effect of this benzene ring is inhibited, okay, by the introducing of the ortho substituent. That is nothing but steric inhibition of the resonance, and simply it is called as a ortho effect. That means here any ortho substituted benzoic acid is more acidic than the meta and para substituted benzoic acids irrespective of its nature actually. Either it is a donating group or it is an electron withdrawing group, that is a more acidic compound. Any ortho substituted compound, that effect is known as a ortho effect. Okay, why? Because here by introducing of the ortho substituent, here this group go out of the plane. So here resonance with phenyl ring, that means plus some effect is stopped. Then here this negative charge is effectively stabilized by this CO group. So here in this case the conjugate base is more stable. Okay, that's why any ortho substituted benzoic acid is a more acidic. That is known as a ortho effect actually. Okay, that means here, for suppose a COOH, simple benzoic acid, here COOH, it is OCH3. Now here COOH, this is OCH3, and next one COOH and at OCH3 at para position. Okay, so here in this case, which is a more acidic, here irrespective of the nature of this group, actually it is a plus M group, but here at ortho position plus M effect is not working. Okay, because of the SIR effect, steric inhibition of the resonance. Yeah, because of this group go out of the plane, so there is no plus M effect of the OCH3 working with benzene. So here 2 is more acidic, and next here third one is more acidic because at meta position minus I effect is working but not plus some effect. Okay, at para position here plus some effect is working because of the electron donating nature of OCH3, its acidic nature decreases. That's why unsubstituted benzoic acid more acidic, and least one fourth. Okay, but here in this case it is ortho effect, SIR effect. Because of the SIR effect, this conjugate base is stabilized by the resonance with CO group. Okay, the plus some effect of the phenyl is not working, that's why it is a more acidic. Okay, that's it. So here in this case at meta position only minus effect is working, so that's why here this is a more acidic because of the minus effect, electron withdrawing nature. So conjugate base slightly more stabilized, that's why more acidic. Here OCS at para position plus some effect is dominating, so here because of the electron donating nature of OCS3, so acidic nature decreases very much than the simple benzoic acid. Okay, that is. Or suppose if it is a methyl actually, yes, COOH, and you see this one COOH, here CH3, and then COOH at meta position CH3, and at para position COOH. Here in this case this is a plus I group. Okay, here plus I effect as well as hyperconjugation effect working. Here in this case plus I as well as plus H, but it is ortho substituted, so 2 is more acidic. Next here plus I effect at meta position, but in this case OCH3 minus I group. Okay, so here in this case one is more acidic. Next here plus I effect is donating nature by the plus I effect lesser, but here donating nature by the plus H hyperconjugation at para position working. Okay, so it is the least acidic, so 3 and 4. Okay, so by the hyperconjugation is working at the ortho position para position as like meta, so that means that mesomeric effect is working at the para position and the ortho position. Here by the hyperconjugation it becomes a very least acidic. Okay, that's the acidic nature order. Or suppose here in case of the NO2 groups. Okay, so just here I am writing simple benzoic acid. Okay, next one here benzoic acid, orthonitro-benzoic acid. Next here COOH at meta position and COH at para position NO2. So here first it is a more acidic ortho position. So next here NO2 minus psi group minus effect at the meta position only, but here NO2 minus M as well as minus psi. So here 4 more acidic, next 3 and least one is a 1 is acidic. Okay, so that is a ortho effect and applications of the ortho effect. Any ortho subject benzoic acid more acidic irrespective of its nature, and then after that we can consider the electronic effects. For the meta derivative as well as the para derivative, we should consider the electronic effects. So based on that electronic effects, we can say the that acidic nature of the carboxylic acids. Okay, that's it. Thank you for watching.